Hi, class. I'm making a review tape of some of the covering some of the questions from the sample test that's, as you know, is posted on the Blackboard page under the sample tests folder. We're not going to cover every problem on the sample test, but I just want to hit a few of the highlight problems on the sample test, but that doesn't mean that other problems from the sample test could not be on the test, just because I don't mention them explicitly in this video. So, of course, remember the test is Wednesday, September 28th, and you can bring a calculator, right, to the test, and your survival card, right, a standard size index card, and you can write on that index card whatever you think would be helpful for you while you're taking the test. Make sure you use a standard size index card, right? So that's one that you can purchase commercially, right? So there's different sizes of index cards, but any standard size is okay, but not an index card that you have made yourself, right? Okay, so let's start here by looking at some of the parts of problem one. So this is a very basic problem where we're just covering, the definitions of vectors in two dimensions and some of the operations with vectors in two dimensions. So make sure, of course, that you're familiar with, that you're familiar with these very basic questions about vectors in both 2 and 3 dimensions. So including making sure, right, that you can plot vectors, right? You can draw the graphs of vectors, not only in 2 dimensions, but later on in the sample test, right? You're also asked to plot vectors in 3 dimensions as well, of course, as we've practiced this in class a lot, and this is a lot more challenging, right? To get a good picture of a graph in a vector in 3 dimensions than it is in 2 dimensions. So make sure you can do that simple sort of question, right? Make sure you can put vectors in either 2 or 3 dimensions, right, in standard form. So that's the I plus J form, right? Okay. And of course, make sure, right, that you can do simple things like compute the magnitude of a vector. So for these 3 vectors that are given in problem 1, u, v, and w here. In this part D, you're asked to compute the magnitude of those vectors. So that's a very basic sort of computation with vectors, right? So make sure you know how to compute magnitudes, because this is an easy question, and surely you'll be asked to compute magnitudes of vectors on a test, right? And you want to get these points correct, right? Don't want to miss those. All right, now let's look at something that's a little bit more complicated, right? And something that you might want to use your survival card for. So in this part E, you are asked to, for each of these vectors, u, v, and w that were illustrated there back at the beginning of problem 1, you're asked to put those vectors in, convert those into unit vectors, right? Sometimes that's called normalizing the vector. So you want to find a unit vector. I don't think any of these are unit vectors, but you want to find a unit vector that's in the same direction, right, as the given vector. And so remember, that's easy to do, right? You just take the vector and divide it by its magnitude. So once you've computed the magnitude of the vector, if you divide both of the components of the vector by that magnitude, then you will get a unit vector, and that unit vector will be in the same direction as the original vector. And we often want to work with unit vectors, and so that's why we learn how to, convert vectors to unit vectors, or so-called normalized vectors. So, for instance, in this first box here in part 1E, right, where we're going to normalize here the vector u, we're just going to take the vector u and divide it by its magnitude. I think in one of the previous problems, we had computed the magnitude of u to be 2 times the square root of 5. And so we just take both of the components of u, right, divide by 2 times the square root of 5, and then you can reduce a little bit, then you get 2 over the square root of 5i plus 1 over the square root of 5 times j. Okay, so there's the unit vector version of the vector u. Okay, now part F is a little bit more complicated still. Okay, because this is something really that that your survival card can really help you with, because one of the things that we're going to have to do for sure on the test, right, is find the direction angle for a vector, right? Remember, in 2 dimensions, the direction angle for a vector is just a single value, right? You just have a single angle, which is the direction angle for a vector. But in 3 dimensions, you have 3 different direction angles, right, for a vector. Okay, so let's find the direction here of the vector. Let's find here the direction of the vector u. And remember, the formula that you want to recall, so this might be something that you want to write down on your survival card, right, is that for any vector, it can be put in this standard form, which is the magnitude of the vector times the cosine of the direction angle for the vector times I, plus, and then the magnitude of the vector times the sine of the direction angle for the vector times j. Okay, and if you take a vector and you think of it as being expressed in this form, okay, then that is what you can use to determine what the direction angle is. Okay, in the following way. All right, so let's think about the vector u. All right, now you really don't have to put u in unit form in order to apply this formula, but in unit form, this formula is easier to apply. And since we already had normalized the vector u back in part E, right? Here's the normalized form, right, of the vector u. Then let's apply this form to find the direction angle for the vector u, right? Okay, so what this formula tells us, right? Okay, if we apply it to the normalized form of u, right, is that this vector is the magnitude of u, right, times the cosine of the direction angle theta times I. So here, the magnitude of u is just, because this vector has been normalized, right? So the magnitude of this vector is just 1. So you can write this standard form as 1 times 2 over the square root of 5 times I, plus 1 times 1 over the square root of 5 times j, because the magnitude of this unit vector is 1. So what that means is, since the magnitude is 1, right, in both of these terms, that tells us that the cosine of theta, right, the cosine of the direction angle for this vector, has to be 2 times square root of 5, right? See, we can think of this formula as being the magnitude of the vector, right, times that, which is 1, times the cosine of theta times I, plus, and then magnitude again, 1 times a cosine of theta times j, right? Which means then that cosine of theta must be 2 over the square root of 5, right? Just like, I'm sorry, this was supposed to be sine of theta times j. And it also tells us, right, that the sine of theta, right, is going to be 1 over the square root of 5. Well, if we know then that cosine of theta is 2 over the square root of 5, right, then that means that theta itself is going to be the arc cosine, or the inverse cosine of 2 over square root of 5. So we just apply arc cosine, right, to 2 over square root of 5, correct, to get theta. And on your calculator, just compute arc cosine or inverse cosine, right, of 2 over square root of 5, and you'll get that this angle measure is approximately 26.57 degrees. So there we get the direction angle for theta is the direction angle for the vector u is 26.57 degrees. Let's check and see if that looks correct. Because we drew a picture of u up here. Oh, there's a picture of u, right? And so this direction angle theta, according to our calculations, there is the direction angle theta, right? That's the angle that the vector forms with the x-axis. So remember, that's supposed to be approximately 26 point, what was it, 57 degrees, right? So that looks about right to me, right? That looks like that angle could be 26.57 degrees, a little bit less than 30 degrees. So that gives me some confidence that my calculations here were correct. Now, you do not have to have the vector written in unit form, right? To apply this formula. You do not have to have the vector in unit form to apply this formula, but it helps, okay? If you already have the vector normalized, right, in unit form, then this formula makes it easy to compute what the cosine and sine of the direction angle are, and then what the direction angle is itself, right, by applying inverse tangent functions. So this formula, I think, is important. That's one that you should put on your index card for sure. May also want to put, of course, how to compute magnitude, right? Okay, if you can't remember, just from practice, if you can't remember how to compute magnitude of a vector, that's pretty easy to just remember. But if you can't remember that, then write that down on your index card as well. Okay, let's try 1G here. So this one may be even a little bit more complicated. No, I don't think so. Okay, because again, it's going to exploit this formula, right? Okay, so here we have a vector z, and we're given that its magnitude is 5, and its direction angle is 150 degrees, right? Okay, so I think that puts the vector z in the second quadrant, right? The z forms an angle of 150 degrees with the x-axis, all right? So we do want to plot the vector z eventually, but before we do that, let's write it in our standard form, the I plus j form, correct? So if you remember this formula, right, that's easy to do, because remember, you can write z in standard form as its magnitude times the cosine of its direction angle times I, right? Plus its magnitude again times the sine of its direction angle times j. Well, we know what the magnitude of z is. It's 5, correct? So we just fill in 5 for the magnitude, right? And then, of course, here, we're not finding the direction angle. We're given the direction angle is 150 degrees. So we fill in cosine of 150 degrees and sine of 150 degrees, right? And then just calculate those. 150 degrees is a special angle, so it's easy to find its cosine and sine. The cosine is going to be minus square root of 3 over 2, and the sine is going to be 1/2, because the reference angle for 150 degrees is 30 degrees. So cosine of 150 degrees is minus square root of 3 over 2. Sine of 150 degrees is 1/2, and then just simplify a little bit, and there you are. There's the standard form of the vector z, minus 5 square root of 3 over 2 times I, plus 5/2 times j. In decimal approximations, this is approximately minus 4.33 times I plus 2.5 times j. The decimal approximation is useful because we wanted to plot the vector z, right? And so you really need to understand better what these coefficients of I and j are, right? Before you can actually plot them. And so let's see what the plot of the vector z looks like. Oh, there it is. Okay, I think something like this. Okay. Indeed, right, in the second quadrant, just as we knew from the direction angle, correct? Okay. So remember that problem A, you may want to work on this for your own edification, but I said you could make this optional on the sample test. And now let's look at not an optional problem though, but a problem that we've seen several examples of already. And this is problem number 2 here, right? Where we have the graph of a function here in the Cartesian coordinate system, right? In two-dimensional space, the graph of this function, x cubed plus x squared minus 3x minus 4, that's a polynomial function. When you graph it, ends up looking like this. Notice the degree of that polynomial function is 3, right? So that tells you that the number of turning points, right, the number of local maxima or local minima for this function is going to be 1 less than degree, which is 2. And there indeed, see, we have 2. We have a local maximum there, and we have a local minimum, right? So we have 2 turning points, 2 peaks and valleys, exactly as we expected, right, from our knowledge of calculus and polynomials on the graph of this function. But that's neither here nor there for this problem, okay? Because what we want to do is find unit vectors that are one that's parallel and one that is perpendicular to the graph of this polynomial at the point minus 2, minus 2. So apparently minus 2 is on the graph of this function. There's the point minus 2, minus 2. Let me see if I can point at it. Yeah, there's the point minus 2, right? And we want to find unit vectors. Does it say unit vectors? Yeah, unit vectors, one which is parallel to the graph of the curve and one which is perpendicular to the graph of the curve. So I try to draw those a little bit here on the graphs. These don't look like they're unit vectors though, the ones that I've drawn. Maybe they are, okay? But when we write them down, we want to write down unit vectors, right? So remember, you really can't, you really can't have a vector that's parallel or perpendicular to a curve, because parallel and perpendicular, these are concepts that apply to straight lines, right? That do not apply to curves. But the way we'll answer this question is by finding a vector that's parallel or perpendicular to the tangent line to the curve, right, at this point. So we'll treat the curve at this point as a line. And the line that you will treat this curve as is the tangent line to the curve right here at this point, minus 2, minus 2. And you know all about finding tangent lines to curve, right? Because that's the most basic problem of calculus, right? Is finding, of differential calculus, is finding tangent lines to curves. That's where differential calculus begins at, right? So how do we find the tangent line? We really don't need to find the equation for the tangent line to the curve at this point. All we really need is the slope of the tangent line at this point, right? And of course, to find the slope of the tangent line, you use the derivative, right? So I took the derivative y prime of x cubed plus x squared minus 3x minus 4. That's a very easy derivative to compute, right? It's just using the power rule. This is just going to be 3x squared plus 2x minus 3. And then if you evaluate that derivative at this point, -2, right, you will get 5, okay? So we know that the slope of the tangent line at the point -2 is pretty steep, right? In the positive direction, you have a pretty steep slope there. It's 5, okay? Now, we can think of this value 5 as being 5 divided by 1, and that's rather informative, right? So that tells us that the slope of the tangent line at this point has a rise of 5, right? When you have a run of 1, okay? Go back to the, this very basic definition of slope as rise over run. And that tells us then that we can create a vector, right? Okay, that is parallel to the tangent line, right? By giving that vector a vertical component of 1 and a horizontal component of 5. So the vector, the vertical, horizontal component of 1 would be 1 times I, or just I, and a vertical component of 5 would be 5 times j, right? So this vector I plus 5j is parallel to the curve at this point, -2, -2. Now, the line perpendicular, right? The line perpendicular to the tangent line will have slope that is the negative reciprocal of, that's the negative reciprocal of 5 over 1. So that would be -1 over 5, right? So if we think of this as, again, as rise over run, we can create a vector that's perpendicular to the tangent line, right? Okay, by giving it a vertical component of -1, right? A rise of -1, and a horizontal component of 5. That is a run of +5. So we get this vector, horizontal component of 5, so that's 5 times I, vertical component of -1, so that's -1 times j. That vector would be perpendicular to the tangent line, or another way of saying that is perpendicular to the curve at the point -2, -2. So there's a parallel vector, there's a perpendicular vector to the curve, but these are not unit vectors. So we want to normalize these vectors, right? And we do that by dividing their components, right, by the magnitude. Well, I didn't show the computation of the magnitude here, but the magnitude of these two vectors is the same. When you calculate it, you will get a magnitude of, when you do the calculations, square root of 26. Did I not show that anywhere? No, I don't think so. So you get a magnitude of square root of 26. And so divide these components by square root of 26. And so there it is shown, right? So you will get unit vectors 1 parallel perpendicular to the curve. Okay. All right. So there are some very basic sorts of questions, basic types of operations that you can perform with two-dimensional vectors. Sometimes also with some of these, of course, also apply to three-dimensional vectors as well. All right. Going to pause here just briefly, and then we'll come back and look at more problems. Okay, we're back. Let's look at one more problem with two-dimensional vectors. And this is a physics application. So, of course, this is maybe a little bit more challenging because it's an applied problem, but it's going to involve, of course, some of the operations that are needed, right, that you need to know for two-dimensional vectors. All right, so here's the description of the problem. Hope you can recall some of these examples from our notes, right, and from the work. So you remember how to approach this problem on the sample test, and if you have a problem like this on the test. So we've got two forces, and the magnitudes of the forces are 80 pounds, right, and 100 pounds, right. Remember, we often measure forces with weight units of measure, right. So we have these two forces acting on objects at particular directions. So one of the forces is acting on the object at an angle of 135 degrees, and the other is acting on the object at an angle of 60 degrees. So I try to draw a really crude picture of this situation. Look down here. This is pretty crude. So here's our object. Here's our object here, and so it's being impacted by. Right, it's being impacted by these forces. Right, so these forces are pushing or pulling on the object. I've sort of drawn it as pushing on the object here. So one force has an angle of 135 degrees with the x-axis. So think of this horizontal line here as being the x-axis, or thinking well, yeah, think of this horizontal line as being the x-axis. So one of the objects is acting, one of the forces is acting on the object, at an angle of 135 degrees. That's the one that has, that's 80 pounds of force, right? And then you have another a force that's acting on the object at an angle of 60 degrees only with the x-axis. And that force is 100 pounds, right? So, of course, these two forces are combining, right? And, to act on the object. And so we want to find altogether, right, the direction, the total magnitude of the force on the object and the direction of the total force, right, on this object. So this is easy to do, right? I mean, at least in theory, it's easy to do, right? Because we're going to treat again each of the forces as a vector, right? And then the total force will merely be the sum of these two vectors. So when you add two vectors together, the sum is called the resultant vector. So what you're asked for is, the direction and magnitude of the sum, the total force, right? The resultant force on this object. So if you take, all you have to do, right, is again, represent each force as a vector, add the two vectors together, and that will give you the total force or the resultant force on the object. So we have to represent both of these forces as vectors. So this vector I'm going to call F1 for force 1, right? And this vector I'm going to call F2. And so remember, it's not difficult to convert forces to vectors because the amount of force is going to be the magnitude of the vector, right? Okay. And then, of course, we're also given the direction of the vector. So we can put both of these forces, right, in standard form using, right, this formula, right, from the previous problem, right, that I kept pointing out, correct, right? That you can write a vector as its magnitude times the cosine of its direction angle times I, right, plus its magnitude times the sine of its direction angle times j, correct? So that's how we're going to construct these two force vectors in this particular situation, right? So for this first force vector, it's just its magnitude, which is 80. That's the amount of the force, right? Times its direction angle, which is 135 times I, right? And then 80 plus the sine of its direction angle, which is 135 again, times j, right? And then it's just a matter of simplifying this expression. And this is not difficult to simplify. You just have to compute cosine of 135 and sine of 135. These are both special angles. So it's easy to compute their cosine and sine in exact terms. Cosine is minus the square root of 2 over 2. The sine is positive square root of 2 over 2. Multiply both these by 80, right, and reduce a little bit. And you get, for the first force, this force, it's represented by the vector minus 40 times the square root of 2 times I plus 40 times the square root of 2 times j. And now we'll do exactly the same thing for the second force, correct, right? Take its magnitude, which is going to be 100, because that's the amount of force, times the cosine of 60, which is its direction angle, as we were told, right, times I plus 100 times the sine of 60 degrees times j. And then you just have to compute cosine of 60 and sine of 60. That's easy to do because these, again, are special angles. So you can compute their cosine and sine in exact form. If the cosine is 1/2, sine is square root of 3 over 2. And then just insert those two trig measures, right, into your formula and simplify, and you get that the second force is 50I plus 50 times the square root of 3 times j. And then the resultant force you get, so that's the total force on the object, right, you get just by adding to the two force vectors together. So just take F1 plus F2, right, which means you just add the I coefficients. So that's minus 40 times the square root of 2 plus 50 times I. right? And then add the j components together, or the j coefficients together. So you get 40 times the square root of 2 plus 50 times the square root of 3 times j. So there's the exact calculation for the resultant force. That's the total force vector that's acting on this object. Now, of course, if you really want to work with this this resultant force vector, you need to find estimates, right, for these two coefficients. So I did that with the calculator. So 50 minus 40 times the square root of 2 is apparently minus 6.57. And then 40 times the square root of 2 plus 50 times the square root of 3 is apparently 143.17 times j. So there is the force vector. And here is its magnitude. Just calculate the magnitude and you get, just using our usual magnitude calculations, right? And you get 143.32, okay? Is the magnitude. So it's 143.32 pounds of force on this that's altogether that's acting on this object, right? 80 pounds from this force, 80 pounds from this force, 100 pounds from this force, but because they're not, because they're acting at these angles, you get a total force of 143.32 pounds. Oh, I see something that I left off here from the answer key. Oh, it says find the direction of the resultant vector. So there's its magnitude, right? But we also want to find the direction of this vector. Okay, so to do that, let's take the resultant vector and let's unitize it, right? Okay, let's normalize it. So let's put it in unit form. So that's easy to do, right? You just take the vector itself, f1 plus f2. Well, let's give this a name so we don't constantly have to write f1 plus f2. So let's call this altogether. Let's call this vector, this resultant vector f. So to normalize the vector f, right? You take the vector and you divide it by its magnitude, right? So we know that's going to be minus 6.57 divided by 143.32 times I plus, and then let's see, the 143.17, right? Over 1.2 times j. Oh, that's very close to one, right? Not quite one. And now, if you use your calculator, of course, you can get decimal approximations, right, for these two coefficients. See what those are. So let's take the calculator here and let's do these calculations. So we get 6.57, right? Change the sign, divide that by 143.32. So that gives me what? About minus 0.46. See that again. So minus 0.046, minus 0.046 times I, and then plus, now let's do this calculation, right? So that's 143.17 divided by 1.2, 140.32, and get very close to 1, approximately point, really rounding off there, it's really 1, right? Times J. So there's the not the resultant force vector, right? But that's the a unitized version of the resultant force vector. Now, to find the direction, right? To find the since you've got this resultant force now in unit form, normalized, right? You can find its direction by following, right? You know that the cosine of its direction vector is going to be the minus 0.46, or its direction vector is the arc cosine of minus 0.6 if we did our calculations right. Let's see if we can calculate that arc cosine, right? So 0.046. All right, change the sign of that so it's negative, and let's try cosine of that and get about 92 degrees. So or a little bit more than 92 degrees, right? 92.63 degrees. So our notice that our force vector, right? Our resultant force vector is acting on this object almost at an angle of 90 degrees. So it's almost acting vertically, right? On not quite, but almost vertically on our object. Yeah, actually 92.64 degrees there. If I had rounded properly to 2 decimal places. Okay, so well, you get a bonus here. I left one answer off of the answer key. All right, now so maybe conceptually a little bit more difficult, right? But is vectors in 3 dimensions, but sometimes not, maybe conceptually more difficult, but sometimes in practice not. The arithmetic is not more difficult in 3 dimensions than it is in 2 dimensions, right? So again, remember, make sure you can at least make a stab, right, at plotting vectors in 3 dimensions. That's not easy to do, right? But see if you can, make at least a decent effort at that. Okay, I'm not going to usually grade you on the test for perfect artistry here, right? Because my graphs are not great either. But at least make a decent effort, right? When you're asked to plot vectors in 3 dimensions. But of course, when you're doing calculations, try to get those exactly correct. So remember, you can calculate magnitude in 3 dimensions, right? Okay, right. So that's almost as easy as magnitude in computing magnitude in 2 dimensions. Remember, we have operations in 3 dimensions, right, that we don't have in 2 dimensions, like dot product. So make sure you know how to compute dot product, right? Okay, so that's very easy. Just take the product of each of the components, right, in your vectors, and then add those products together. So there's the calculation. I don't need to go back through this computation, but there's the calculation of dot product of u and v, right? U dot v for these two vectors u and v here, right? And then also remember, a little more difficult, however, right, is finding cross product, right? Okay, but this is a very useful computation for us. But make sure you practice with cross products and make sure you include whatever you need to, right? On your make sure you include whatever you need to, right, on your index card, on your survival card. So that you'll be able to compute cross products. Okay, let's see. So in computing the cross product of V and Q, right? Make sure that you, well, not make sure, but what's helpful is constructing this little matrix, right? This little three-dimensional table, correct? Where the first row is just I, J, and K. The second row is are the coefficients of first vector in your cross product, right? And the third row are coefficients of the second vector, right, in your cross product. And then remember how to use that table, right, to compute the coefficients in the cross product. Like, so for instance, if you want to compute the coefficient of I, want to think of yourself as sort of blocking out this row, right? Okay. And then computing the cross product here of the coefficients on J and K, right? So you would take minus 4 times 1, right? And then subtract off minus 6 times 0, which is 0. So you get minus 4 minus 0 times I. That's the coefficient of I cross product. And then do the same thing, right? Adding this first column back, but eliminating the second column, and then adding the first two columns back and eliminating the third column, right? To compute the coefficients of J and K in cross product. So make sure you've gotten lots of practice with computing cross product so you can do that efficiently, get the answer right on the test. You don't want to make a mistake on computing a cross product because even though there are some steps in computing a cross product, it's all very elementary arithmetic, right? And so you don't want to miss that. Test. Now, where do we use cross products and dot products? Okay, and in 4C is an example of where dot products, for instance, are useful because that allows us to calculate the angle between two vectors. One thing to remember, one important thing to remember, right, that we've mentioned a few times is that if you compute the dot product of two vectors, right, and that turns out to be 0, right, remember that means that the two vectors are perpendicular, right? So when the cross product is 0, I'm sorry, when the dot product is 0, you have perpendicular vectors. But when the cross product is 0, right, that means you have parallel vectors. So don't forget that. Don't forget that little fact. Well, I don't think that these two vectors U and Q are perpendicular to one another. Let's see if we can find the angle between vectors U and Q. Let's see, what does that look like here in our picture if I drew a halfway decent graph? So there's the vector U, right? And here's the vector Q. But these are both slightly elevated above the XY plane. So U is pretty obviously elevated, right, above the XY plane. I think it's over here in the terminal point here is over here above. I don't know what what quadrant is that? Okay, I'm not sure. I can't tell what the. It's hard for me to read my tick marks here. Is this the first quadrant? I think so, right? So the terminal point of view here is floating here above the first quadrant. The terminal point of Q is over here, so that would be the third quadrant, right? But nevertheless, we're trying to find what's the angle between these two vectors, U and Q. And that turns out to be really easy to do because we have a very nice formula, right, for computing the cosine of the angle between two vectors. So here is another formula, right, that you may want to add to your index card. So the cosine of the angle between two vectors, right, is the dot product. This is in 3 dimensions. It's the dot product of the vectors, right, divided by the product of their magnitudes, correct? Okay. So if we know the dot product of U and Q, and we know the magnitudes of U and Q, right, we just take that quotient. we may have already computed in one of the earlier examples, we may already have computed u dot q, did we already compute that? Oh yeah, it's minus 74 here, up here, okay? And I'm not sure if we had already computed the magnitudes of u and q. I don't see it, but it's easy to compute the magnitudes of both the vectors u and q, right? So the magnitude u turns out to be square root of 88, and the magnitude of q turns out to be square root of 86. And when you simplify this and estimate with the calculator, you get about minus 0.85, right? And so that's the cosine of the angle between the two angles. And then just take the arc cosine, right? And that gives you 148.28 is the angle. Looks about right, yeah. So I think our graph here is not too bad. That certainly looks like that could be 148 degrees, right? In that picture. Okay, so remember how to find the angle. Remember how to find the angle between two vectors, right? Either in 3 dimensions or 2 dimensions. Let's see. Oh, did we already find the angle between two vectors in 2 dimensions in one of the earlier problems? Was that problem? Oh no, we didn't do that in 2 dimensions, right? Okay. But you can also find the angle between two vectors in 2 dimensions as well, correct? I think it's the same formula, right? Okay. Now let's now one thing that one operation that is a little bit more complicated, right? But you're going to have to recall this one is how to find the projection of one vector onto a given vector. So if you're given 2 vectors u and v, remember one operation that we have to perform time is finding the projection of the vector u, or I'll sometimes call the well, no, just the projection of the vector u onto the vector v, right? Or you can also, and vice versa, find the projection of v onto u, correct? But in this case, we want to find the projection of u onto, projection of u onto v, okay? And so there's a formula for that, correct? So this is another formula that you might want to write down on your index card, right? The projection of one vector onto another vector, okay? So the formula sort of looks like the angle between the two vectors, right? But remember, a projection is a vector, so what you're going to end up with when you compute a projection is a vector, okay? So you take this coefficient and then multiply it by the vector v, and that gives you projection of u onto v. So I'm pretty sure this formula you're going to have to recall, and so you may want to write down that one on. May want to write that one down on survival. All right, so I didn't go through all the calculations here, but you can follow them on the answer key for finding projection of to v. Now, one place that cross products are useful, okay, is is illustrated here in part 4E, right? Because you're asked to find a vector G that's orthogonal to 2 given vectors. So you're given 2 vectors. In this case, we're given the vectors v and q, and we want to find a third vector G that's perpendicular to, orthogonal to both of these vectors. This is going to be very important in helping us write down formulas for equations for planes in 3 dimensions. All right, so that's why this fact it turns out to be important to us. But it's a very easy thing to find this orthogonal vector because it's just the cross product. So when you take the cross product of 2 given vectors, you take the cross product of two given vectors, that gives you a third vector, which is orthogonal to the 2 given vectors. So all we have to do here in this problem looks like a complicated problem, right? And there's a lot of blank space there, apparently, to solve this problem, but it's not a complicated problem at all. All you have to do is find the cross product of B and Q. And we had already calculated, don't forget earlier, the cross product of V and Q. There it is. So all we have to do is write down our earlier answer. We calculate that cross product. So this vector is apparently perpendicular to both of the vectors V and Q. So don't forget that very important fact, right? You want to find a vector which is orthogonal to 2 given vectors, perpendicular to 2 given vectors, just take the cross product. Now, another thing that's for 3 dimensions that we also do in 2 dimensions, but it's a little bit more complicated, is find direction angles, right? So if you have a vector and you want to know the direction of the vector, that's something that we often want to calculate, right? In 2 dimensions, the direction, though, is just a single angle, right? It's the angle between the vector, the angle formed between the vector and the x-axis. But things are more complicated in 3 dimensions, unfortunately, right? In 3 dimensions, we have to give the direction of a vector in terms of 3 angles, not just 1 angle. So you have to find the angle that the vector forms with all 3 axes to completely specify the direction of a vector in 3 dimensions. So you have to find the angle that the vector forms with the x-axis, the angle that the vector forms with y-axis, and the angle that the vector forms with z-axis. And you need all 3 pieces of information to accurately describe the direction of a vector in 3 dimensions. So 1 angle, unfortunately, is not just enough. So usually we label alpha as the angle that the vector forms with the x-axis, and we label beta the angle that the vector forms with the y-axis, and we label gamma, this is the Greek letter gamma, as the angle that the vector forms with the z-axis. But it's not difficult to find these angles with a little bit of trig because we have formulas for them. So it turns out that the cosine of alpha is just going to be the I component, the first component of vector, divided by the magnitude of vector. And the cosine of beta, the angle that the vector forms with the y-axis, is just the second component, the j component of the vector, divided by the magnitude of the vector. And gamma, the cosine of gamma, I left off cosine. So cosine of gamma is going to be the third component of the vector, the z component of the vector, I'm sorry, the k component of the vector divided by the magnitude of the vector. So for this vector v, if you recall from one of the earlier parts of this problem, its I component, its first component is 5. Its magnitude is square root of 41. So that means that the cosine of the angle that this vector forms with the x-axis is just 5 over the square root of 1. And then just find the arc cosine of that, of course, to get the angle alpha. That turns out to be, using a calculator, 3866 degrees. For the cosine of beta, it's going to be the j component, right, of the vector, right, which is -4 divided by the magnitude, square root of 1. Or in other words, beta is the arc cosine of this value. That turns out to be 128.66. And then a gamma is especially easy to calculate because you take the z component, I'm sorry, the k component, which corresponds to the z-axis, right? The k component of your vector, which for the vector v was 0, it did not have any elevation above the xy axis. It's k component of 0. Divided by the magnitude is still 0, right? So you get gamma is the arc cosine of 0, which is 90 degrees. Okay. So there you have it. There are the three direction vectors for, I'm sorry, the three direction angles for this vector V. So you probably want to remember these formulas, right, for the test, correct? How do you find three direction vectors? I'm sorry, the three direction angles for a vector in 3 dimensions. Okay, let's get down some more here. I can get the, yeah, oops. And now, let's look at problem 9. Okay, so now this is some of this is a question of something that's related to things that we've been doing a little bit more recently, and that is finding equations, right, for lines in 3 dimensions. So we've been discussing that in the past couple of days. So this is a little bit less familiar to you, some of the other problems from the sample test. Let me pause here for just a moment and come back and look at how to find equations for lines, right? And then also planes, right, in 3 dimensions. All right, let's look at just the very basic problem of writing down equations for a line in 3 dimensions. And just like in 2 dimensions, of course, you're going to need some information about the line, right? Okay. And in 3 dimensions, the key information you need is a direction vector for the line. So you need to know a vector that's in the same direction as the line. And then you need, of course, to know a point that the line passes through. So this is analogous to, in 2 dimensions, to write down an equation for a line, you need to know the slope of the line, because that gives you in 2 dimensions, right, the direction of the line. And then in 2 dimensions, you also need a point that the line passes through. In 3 dimensions, instead of the slope, you need to know a direction vector for the line, not just a single slope value, but a direction vector for the line, and then a line, and then a point that the line passes through. But direction vector in 3 dimensions is analogous to slope in 2 dimensions. So let's look at this problem 9a and see how we get this information that we need, right, to write down the equation for the, or equations as it turns out, for a line. So here we're given 2 points that the line passes through, just like in 2 dimensions. If you know 2 points that the line passes through, right, you should be able to write down the equations for the line in 3 dimensions, because in 3 dimensions there's still only one line that passes through any 2 given points, right, in 3 dimensions. So let's see, how do we use this point information to find our direction vector and then the equations for the line? Well, obviously, right, you find the direction vector simply by finding the vector that connects these 2 points, right? So you use one of these points as the initial point, one of these points as the terminal point, and then find the vector that connects these 2 points, with this initial point and with this terminal point. And that's easy to do, right, just by taking the difference in the coordinates of the points, correct? So you get that the direction vector for this line is going to be 6, 11, 4. Here it is written in component form, but of course you could write that in standard form as well, as 6i plus 11j plus 4K, right? And then once you've got the direction vector, right, the components of the direction vector and a point, you only need one point, a point that the line passes through, so you can use either one of these 2 points, right? Then you can write down either the parametric equations for the line, which look like this, right? Or the symmetric equations for the line that look like this, right? How do you write down the parametric equations? Well, you simply take the coordinates of one of your points, right? Say 3, 0, 2, since that's the first point that we're given here, right? And you write them, those coordinates, into your 3 parametric equations, right? X equal to X coordinate of this point, Y equal Y coordinate of this point, Z coordinate of this point. And then you add on in each case, right, the components of the direction vector times this parameter t, right? This extra variable t. So the first parametric equation, right, for this line would be x equals 3, this coordinate, plus this component of the direction vector 6 times t, right? The second equation would be y equals 0, right? The y coordinate of this point, right, plus the y component, right, of your direction vector times t, right? 0 plus 11t, though, just turns out to be t, right? And then z equals the z coordinate, right, of your point, plus, and then the z component, right, of your direction vector plus t. So very easy to write down the parametric equations. And also the symmetric equations, right? You just write x minus the x coordinate of your point that you're given, right? Which in this case is 3 divided by the x component of your direction vector, equal y minus the y coordinate of the point that you're given, which is 0 here, right? Divided by the y component of your direction vector, equals z minus the z coordinate of the point that you're given, divided by the z component, right, of your direction vector. So either of these are accepted forms of equations for lines in 3 dimensions. If you want to find, if you want to generate other points on the line, right? You know 2 points on the line, but if you want to generate other points on the line for whatever reason, so if you want more points on this line other than these 2, you can generate those easily, right? So you can generate infinitely many points on your line just by using your parametric equations. I think it's easier to use the parametric equations and substituting different values for t here, right? See, notice if you use t equals 0, you get 0 for each of these second terms. That gives you the point 302. That's this point that we already knew that was on the line, right? But if you use different values for t, positive or negative, any value that you like for t, plug that value for t into these 3 equations, you'll get different, you'll get coordinates for different points on this line. So you can generate infinitely many points, right, on this particular line using the parametric equations. Very easy to do. Now, so unfortunately, right, as we've talked about in class, equations for lines in 3 dimensions are a little bit messy because it involves, unfortunately, multiple equations, right? You don't get just a single equation for a line in 3 dimensions, but that's not true for planes, right? Planes in 3 dimensions, you do get a single equation that you can use to create a plane in 3 dimensions, right? And so how do we do that? What information do we need to know to write down a plane as opposed to a line? So a plane surface, right, in 3 dimensions. What information do we need? And so it turns out you need to know, again, of course, a point that is on the plane. You need to know a point that's on the plane. And you need to know also a vector that's perpendicular to the given plane. So not a vector parallel to the plane, but a vector that's perpendicular to the given plane. Those two pieces of information are all you need to write down the equation, single equation for a plane in 3 dimensions. This vector that's perpendicular to the plane, any vector that's perpendicular to a given plane is called a normal vector for the plane. It doesn't have to be a unit vector, but it could be. So you need to know any normal vector for the plane, any vector perpendicular to the plane, and then a point that the plane passes through, and you can write down the equation for a plane in 3 dimensions. So planes in 3 dimensions are a little bit similar to lines in 2 dimensions. That kind of makes sense, right? Lines are sort of 2-dimensional objects. Planes are kind of 3-dimensional objects, right? That's why planes in 3 dimensions are kind of analogous to lines in 2 dimensions. And we're going to use planes in 3 dimensions kind of like we used it for our calculus purposes. We're going to use planes in 3 dimensions kind of like we use lines in for 2-dimensional calculus. All right, so all right, all that is all just is just extra explanation there. How do we actually do this problem, right? So if you're given, for instance, 3 points that a plane passes through, right? You're given 3 points that a plane passes through. How can we find the equation for the plane? Okay. Well, remember, what information do we need? We need a point that the line passes through, that the plane passes through. Well, we have 3 points here, so we've got way more points than we need, right? We've got 3 points here, but we also need this vector that's perpendicular, or also called orthogonal, to the plane. So that's the hard part, right? How do we find the vector that's orthogonal, perpendicular to this plane, so we can write down the equation for the plane? The answer is as follows, right? Let's find a vector that connects these 2 points and these 2 points. So I'm going to find 2 vectors here that are in my plane. Okay. You could arrange the points differently, but I think in this example, we're going to find the vector, as I mentioned here, that connects this point with the second point and this point with the third point. But you could have found other combinations of these points to find different vectors connecting these points. These are just the vectors that I chose to concentrate on. So I'm going to call U here the vector that connects the first and the second point. Okay, so this is the vector U. And then I'm going to call the vector V the vector that connects the first and the third points. Okay. So there I did. I just very easily calculated these vectors connecting these points. First one I called U, the second one I called V. And here are these vectors in standard. Here are these vectors in standard form. So the vector U is AJ minus K. The vector V is 4I plus 5J minus 4K. So these 2 vectors are not orthogonal to the plane. These 2 vectors actually fall in the plane, right? Because they're connecting points that are contained in the plane. So these vectors are actually parallel to the plane because they actually fall in the plane itself that's being described here. But we want a vector that's perpendicular to the plane. So all we have to do is find a vector perpendicular to these 2 vectors that are in. And that, of course, is the purpose of a cross product, right? So if you compute the cross product of these 2 vectors that are in the plane, you will get a third vector that is perpendicular to both of these vectors. And that vector will also be perpendicular to the plane because these 2 vectors fall in the plane. So you just find the cross product of U cross V. That will be your normal vector. It doesn't have to be a unit vector. It does not have to be a unit vector. Any perpendicular vector will do. So I didn't show the calculations here, but if you do U cross V, get, I think, if I did this right, minus 27I minus 4J minus 32K. There is your normal vector Now, how do you use the normal vector to write down formula for the line? Here's the formula for the line. Just take the I component of your normal vector and then multiply it by x minus the x coordinate of one of the points that you're given in the plane. So I used the first point. We could have used this point or this point. So we got minus 27 times x minus a minus 3, because this x component is this x coordinate is minus 3, right? That turned out to be x plus 3. Then take the j component, right? Multiply it by y minus the y coordinate of your point, right? So you get y minus a minus 4, which is y plus 4. And then take the k component, right, of your normal vector and multiply that by z minus z coordinate that you're using that's in the plane. So you get z minus 2 here. Set that equal to 0. So there it is. There's the equation for your plane. Okay. So solutions to this equation in 3 dimensions. Of course, those are points in 3 dimensions, right? Because you have to have an x a value, a y value, and a z value. Solutions to this equation will be points that fall on this plane. Okay. Of course, there are infinitely many solutions to this equation, but when you graph all of them, you get a plane. Okay. In 3 dimensions, you get a plane that contains these 3 points. Basically, it's just that easy to write down the formula for a plane in 3 dimensions. You need to know a normal vector and a point on the plane. Now, sometimes determining the normal vector or sometimes determining the point on the plane is the tricky part, right? But if you have those 2 pieces of information, you'll be able to easily write down formula for a plane in 3 dimensions. Okay, now there are a couple of other problems here on the sample test that but I want to do them that I wanted to look at, but we're going to do this in class, I think, on Monday, because we haven't talked about this yet in class, so I don't want to do it on the sample test yet. So we'll do these problems in class, actually. One of them is problem 11, which, how do you find the distance between a point and a plane? That means the shortest distance, right? Between a point and a plane. We know how to find the distance between 2 points in 3 dimensions. That's just the 3-dimensional distance formula. But how do we find distance between a point and a plane? When you say distance between a point and a plane, of course, there are lots of distances between a point and a plane. We mean the shortest distance. So how do we find the shortest distance between a given point and a plane, assuming that the point does not fall in the plane? If the point falls in the plane, then the distance is 0, right? But if you have some plane and some point outside of that plane, how do we find the shortest distance between the point and the plane? And then, of course, how do we graph planes, right? Okay, they're the really simplest surfaces in 3 dimensions to graph are planes, but how do we actually do that efficiently, right? Because it's not easy to graph a surface in 3 dimensions, and not even planes, which are the easiest surface to graph in 3 dimensions, are particularly easy to graph. Of course, more complicated surfaces in 3 dimensions are going to be even harder to graph, right? So how do we try to graph a plane in 3 dimensions? That's the point here of problem number 12, and look at that in class also. You can't do it perfectly, but I'll show you the shortcut here for how to try to efficiently, without doing too much work, try to draw a picture that kind of looks like a plane, the plane that you're given to graph, right? Okay. All right, so let me stop there. I think we've eaten up a lot of time already on this video, so this is going to already be a pretty long video. So let's quit there, right? And I hope that's helpful for you for your test, right? Again, remember to work on that index card, write down things, your survival card, right? Write down things that you need to know on there, because I think that's going to help you when you take the test, all right? So I'll see you back in class.